Today's lecture is on chapter 9.1 to 9.3 on gas laws. So if we take a look at our different phases of matter, we have our solids and our liquids, and then we have our gases. And so we've discussed a little bit about chemical reactions for aqueous solutions, and we've talked about precipitation reactions involving solids. So let's get into a little bit of the chemistry of how we can understand how gases actually behave in nature. So gases play an important role in almost everything that you can imagine. So whether we're dealing with industrial synthesis through chemical vapor deposition to medical treatments to talking about disruption in our atmospheric gases causing smog pollution, or just the maintenance of our planet in general through the various layers of gas within our atmosphere. Gases are incredibly important to our existence on Earth. And so we can see that the composition of dry air at sea level shows that we are mostly composed of nitrogen gas and oxygen gas on our planet. And that to a smaller extent here, we have argon, carbon dioxide, neon, etc. And so we know that through, we're going to talk a little bit more later in an upcoming class here about the ramifications of disruption of the gas layer on our planet, known as global warming. But so we, just to kind of preempt that conversation a little bit, it has to do in part to a disruption in our CO2 levels on Earth. And so we can see here that carbon dioxide only actually takes up a very small fraction, so 0.04 approximately percentage of our overall gas composition in our atmosphere. But small changes in that CO2 level can actually have a very large effect on the overall ability to retain and reflect heat on our planet. So again, we'll talk about that in more detail in a couple classes. So let's discuss the chemistry of gases. So gas is a state of matter where the constituent atoms or molecules have little interaction for one another and are therefore free to move about in whatever volume is available. So mixtures of gases are always homogeneous, which means that you can't tell the difference between the different gas molecules. So if we see a gas here, we can't see it. Everything just looks like it's just these tiny molecules that are all bouncing around that we can't see. And that the one of the reasoning that gases are so homogeneous is because there's little interaction between these gas molecules. They're not chemically interacting with each other, so they're bouncing off each other with elastic collisions, and they just keep bouncing off any hard surface and continue to move around. So gases are compressible. So upon the addition of pressure, the volume of a gas contracts. So less than 0.1% of a volume is actually of a gas is actually taken up by these gas particles. So therefore, it's mostly empty space. So if we picture a vessel here on the board, so we have a vessel that has a retractable piston. Okay, so this is a piston on top that can contract inward. All right, and say we have 10 gas molecules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so these gas molecules are all going to be moving around in their own free direction, and they're going to go whatever direction they want at as fast of a speed as they can go, depending on the amount of thermal energy that allows them to move around. But you can see that these gas molecules are really small in comparison to the amount of empty space. So if we push down on our piston here and compress the total amount of volume in the vessel such that the piston is now at a much lower level, we can still see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our 10 gas molecules are still within this space. They just now have a contracted volume where they are allowed to move around, which means that they're going to then collide more with each other and collide more with the walls. Okay, but we can see that this compression of gas is possible just because most of that gas is empty space. So compression doesn't actually change the molecules at all. It only changes the amount of relative empty space. Okay, so when we discuss gases, we usually think of a couple different terms when we think of gases, and one of the key terms is pressure. So pressure is defined as the force over the unit area. Okay, and so if we think about, so in that previous discussion that I had of gases, I talked about how those gases are going to move around freely and they're going to bounce off each other and they're also going to bounce off the walls of a certain container. And so you have to think about there's a force associated with those particles, even though they're very small particles. There's a force associated with each of those collisions against the edge of a container. And so that amount of force of those gas particles hitting against the sides of a container divided by the unit area of those outer walls gives us our pressure. And so we can express pressure in many different units. For example, there's atmospheres, millimeters of mercury, torr, bar, pascals, and then a pascal divided by 1,000, which is a kilopascal. Okay, so it's very important that we're able to easily convert between all of these different units of pressure because they are all, depending on which sort of agency is giving out a pressure reading, they're going to give a different pressure readout. You'll also see sometimes PSI, which is pound per square inch. That's also a unit for pressure. So let's practice real quick if given these conversion tables to convert between two different pressure units. So, given this problem, the lowest barometric pressure recorded in the United States during a hurricane in 1935 was 669.3 millimeters of mercury. What is this pressure in atmospheres and in kilopascals? So, given the conversion factors shown on the right-hand side of the table, pause your video and work through these conversions. Okay, so our first conversion here, we have our measured value, 669.3 millimeters of mercury, measured value over 1, and we see our conversion factor here showing that there's 760 millimeters of mercury per 1 atmosphere. And so when we plug and chug here, we get a value of 0.8807 atmospheres of pressure. Okay, next we want to convert between our millimeters of mercury and kilopascals. And so if we take a look at our conversions here, we don't have a conversion factor that directly goes between millimeters of mercury and kilopascals or even pascals. But what we do see is a conversion factor between atmospheres and pascals. So therefore, we can use our answer here in atmospheres, convert that to pascals, and then convert pascals to kilopascals. All right, so we take our measured value here in atmospheres, 0.8807 atmospheres over 1. Our conversion factor, showing that there's 101,325 pascals per 1 atmosphere. And we know that our conversion factor, we have 1,000 pascals per 1 kilopascal. And we get a final answer here of 89.23 kilopascals. So we can see that this answer corresponds to answer B on our clicker question. Okay, next, let's discuss how we're actually able to record what's called atmospheric pressure. Okay, so if you ever look at the weather and you will see that there is a reading of pressure that they call atmospheric pressure that will be in either millimeters of mercury or in inches of mercury. Okay, and so this atmospheric pressure that can be reported with the weather will give us information as to incoming weather patterns and what sort of weather we can expect for the day. And so by taking a look at the changes, the trends in atmospheric pressure, whether atmospheric pressure is going up or atmospheric pressure is going down, we can get information as to whether we can expect it to be a sort of clear, sunny day or whether we expect it to be a day that brings precipitation. Okay, so how do we actually, what is this atmospheric pressure in millimeters of mercury? What does this millimeters of mercury mean? Okay, and so let's take a look at this. On this slide here, we have a vessel here that will give us a readout of atmospheric pressure in millimeters of mercury. Okay, so what we have here, the way that we perform this sort of measurement is that you have a tube. We have a tube that you'll fill up completely with mercury, and then you would overturn that tube into a lower dish of mercury. And then, so there is atmospheric pressure pushing down on this tube of mercury. And so what's going to happen here is this atmospheric pressure the force of this atmospheric pressure will cause mercury to be pushed up to a certain level on this tube. And so the distance in which this mercury has been pushed up the tube is dependent on the overall atmospheric pressure. And so we can see that small changes in atmospheric pressure will change the height in which this mercury column will go up. And so what does atmospheric pressure actually mean? How do we get atmospheric pressure? So let's take a look at an image. So if we think about our Earth, okay, so we have our Earth, and the outermost layer of our Earth we call our crust. And then so our Earth has several different layers of atmosphere on top. Okay, we have our troposphere, our stratosphere, mesosphere, et cetera, et cetera. We have these different layers of our atmosphere that go out from the crust. Okay, and so our layers of atmosphere are going to be composed of gas. And so if you think about if you were to blow up a balloon with gas, that balloon is not going to weigh very much, but it does have a slight weight to it associated with the gas that you've blown into it. So think about miles and miles and miles of gas going upwards in our atmosphere. So all of that atmosphere is composed of gas molecules. So that miles and miles of gas have an associated weight that's pushing down onto our crust of the Earth, and in essence, pushing down onto us. So if we have a measurement for millimeters of mercury, where we have our dish with a tube on top, that atmospheric pressure is feeling all of the pressure of our atmosphere pushing down, of all that gas in the atmosphere, pushing down onto that mercury dish, which causes the mercury to go up into our tube. And then so local variations in atmospheric pressure in our lowest troposphere layer here, associated with weather squalls, will give us those slight differences in the height of that mercury stream to give us idea of our weather. So let's take a look at another way that we can measure pressure. And so that was last setup was the way that we can measure atmospheric pressure. Let's take a look at the way that we can measure pressure within a closed container. So if we take a look at this, this open UN manometer, this gives us a way to measure the amount of gas or the pressure of a gas within a closed bulb. So if you have a closed bulb and you screw it into this stopcock, you can go into this open end, so we can see one end is open to the atmospheric pressure, and then we have an open end U manometer. And so you can see that we have mercury that is in this U tube. Okay, and so when we open up our stopcock here, we're going to have basically a comparison of the pressure of gas within this bulb versus the atmospheric pressure on the outside. So if the pressure of this bulb is less than the pressure in the atmosphere, then the atmospheric pressure is going to push that mercury down to a lower level on the atmospheric side and a higher level on the side of the bulb. Whereas if the pressure inside of this glass bulb is higher than the atmospheric pressure, when we open up the stopcock, we can see that the mercury is pushed down to a lower level on the bulb side, and it's at a higher level on the atmospheric pressure side. So the distance between the two levels of mercury can give us information in millimeters of mercury what the pressure difference is from the atmospheric pressure to the pressure within that bulb. And so if we have an accurate measure of our atmospheric pressure, we can do a subtraction saying that the atmospheric pressure minus the pressure in the bulb is going to give that millimeters of mercury difference. We can actually do that simple math to determine what the pressure of the unknown gas solution is. Okay, so let's take a look at one of those problems and have you try to figure out if the pressure in an open gas container that is connected to an open-end U manometer is 795 millimeters of mercury, and the pressure of the atmosphere at the open end of the tube is 742 millimeters of mercury. The level of the mercury in the tube will be what answer? And so just a quick note here, B is not the correct answer. This is just the note for my answer key here on my notebook. Okay, so the correct answer is not B, okay, or not necessarily B. All right, so pause your video and work through that on your own. Okay, let's take a look. So if we're taking a look at our setup here, so we have our bulb hooking up to our manometer, open at the top, and have our stopcock there in the middle. We know that we have 795 millimeters of mercury in our bulb, and we know our atmospheric pressure is 742 millimeters of mercury. So since we see that this 795 is higher pressure than our external pressure, or atmospheric pressure, we know that the mercury level is going to be lower on the bulb side than it is going to be on the open side. So we know that the mercury is going to look like this. So now we need to determine what is the distance difference between those two mercury levels. So for that, we simply do a subtraction problem, saying that 795 millimeters of mercury minus 742 millimeters of mercury is going to equal the difference between those two layers, which is going to equal 53 millimeters of mercury, difference between the two, and we're going to see it higher on the open end side. All right, so therefore our correct answer is A, 53 millimeters higher in the open arm to the atmosphere. Okay, next. When we're discussing gases, we have two sort of considerations for the behavior of gases: an ideal gas and what we call a quote unquote real gas. So an ideal gas is a gas whose behavior follows the predefined gas laws exactly. Whereas a real gas is a gas that slightly varies from the predicted behavior of our predefined ideal gas laws. Okay, so whether we're talking about an ideal gas or a real gas, it's important for us to know that the physical properties of a gas can be defined by four different variables. So pressure, which we've already discussed, which has a symbol of P; temperature, which has a symbol of T, and typically when we're working with gases, our temperature is going to be in units of Kelvin. So again, that's degrees Celsius plus 273.15. We're going to be dealing with volume, which is typically in liters, and number of moles, which is N, which will have units of moles. So the behavior of gases really is quite obvious based on observations that we make on a daily basis in our real life. So for example, if we take a balloon at room temperature and increase the pressure all around the outside of it, what happens to the volume? Okay, so think about a balloon and you push in on it. What's going to happen to that volume? It's going to get smaller, right? So if you have a compressible vessel that's in, you can put pressure and decrease volume. So if we take a balloon and decrease the temperature, what happens to the volume of the gas? So think about a balloon we blow up with air and then we stick it in the freezer. After a while in the freezer, if we take it out, is it going to get bigger or smaller? It's going to get smaller. So we know when we decrease temperature, it gets smaller. Same sort of thing, if we were to put it in the oven, that gas is going to expand and get bigger. Thirdly, if we take a hollow metal sphere with gas in it and increase the temperature, what happens to the pressure? Okay, this is a bomb. If you take a steel container, put gas in it, you heat it up, eventually that pressure is going to build up so high that it's going to explode and send shrapnel everywhere. Okay, so we have these very clear relationships between temperature and pressure, between temperature and volume, and between temperature and pressure in a fixed volume container as well. So we have all of these different sort of observations from our daily life that we can assign different equations to sort of define. So there are three baseline equations that you need to know that kind of define these observations that we can observe in daily life. So the first is Boyle's law. So Boyle's law states that volume is inversely correlated to pressure when you have constant number of moles and constant temperature. Okay, so this is talking about how the volume, so the volume of that balloon changes when we increase the pressure. Okay, so when we increase the pressure on that balloon by squeezing it, so increasing the pressure, we decrease the volume, so inversely related. So we can rearrange this equation to say that the pressure times volume is equal to a constant, such that the pressure and volume initial is equal to the pressure times volume final. So if we think about that balloon analogy, if you have your balloon without any forces put on it, it has associated pressure and volume associated with it. But if we increase the amount of pressure, we're going to see our final volume is going to decrease proportionally. Okay, so a similar sort of equation to our M initial, V initial equals M final, V final. Okay, so we have P initial, V initial equals P final, V final. So let's work through a couple problems here that use Boyle's law. Okay, so I will set you guys, so pause your video and try to work through both of these. So these should be very straightforward problems for you, especially after your experience working with our molarity dilution problems. So pause your video. Okay, first problem. So what is the volume of a 1.0 liters of helium gas initially at 1.02 atmospheres within a balloon after you increase pressure to 2.5 atmospheres at constant temperature? Okay, and that C then again is going towards my, that's my code for my key. Okay, so we have our P initial times V initial is going to be equal to our pressure final times volume final. So we're trying to solve here for our final volume. So if we rearrange our equation, we can find that the volume final is equal to our initial pressure times our initial volume over our final pressure. So if we input our values here, we can see if we started out at 1.02 atmospheres and we started off at 1.0 liters, and if we're going to a final of 2.5 atmospheres, plug and chug, we get a final answer of 0.41 liters, showing two significant figures, which matches our lowest number of sig figs in our starting problem. Next, what is the pressure of 2.5 atmospheres of carbon dioxide gas once you increase the volume from 1.5 liters to 2.5 liters at constant temperature? Okay, so again here, we're going to deal with our P initial, V initial is equal to P final times V final. And here we're solving for P final. So we rearrange the equation, stating that P final is equal to pressure initial times volume final. Plug and chug, 2.5 atmospheres times 1.5 liters over 2.5 liters is going to give us a final pressure equal to 1.5 atmospheres. Okay, so very straightforward problem for Boyle's law. Next, Charles' law. So Charles' law states that the volume and temperature are directly proportional at constant number of moles and constant pressure. Okay, so this is talking about if we took our balloon and we put it in the freezer, which decreased our temperature, we would see the volume also decreases. If we take our balloon and put it in the oven, we increase our temperature and we see the volume goes up. Okay, so we can rearrange this relationship and say that the volume over the temperature is equal to a constant. So therefore, the initial volume over the initial temperature is equal to the final volume over the final temperature. And note here that all of these temperatures must be in Kelvin, which is degrees Celsius plus 273.15. So let's work through a Charles law problem real quick. So what is the volume of 1.5 liters of O2 gas in a balloon once you decrease the temperature from 25 degrees Celsius to 0 degrees Celsius at constant pressure? So pause your video and work through that. Okay, Charles' law states that if we have an initial volume over the initial temperature, that will equal our final volume over our final temperature. And we know our temperatures here have to be in Kelvin. So we want to rearrange and solve for our final volume is going to be equal to our initial volume times our final temperature over our initial temperature. So plug and chug here, we can see 1.5 liters times our final temperature. So that's going to be our 0 degrees plus 273.15, which is going to be 273.15 Kelvin, over our initial temperature, 273.15 plus 25 degrees Celsius, which is 298.15 Kelvin. Plug and chug, we see that our final volume here is going to be equal to 1.4 liters. Okay, very straightforward conversion problem. Next, Avogadro's law states that the volume and number of moles are directly proportional when we have constant temperature and pressure. Okay, and so if we increase our amount of gas within a solution, if we increase the amount of gas within a certain vessel, we're going to see that the volume is going to increase as long as our temperature and pressure are the same. Okay, so the more moles of gas, the more space it's going to take up. Okay, the less moles of gas, if you remove some gas, so think about a balloon. The more you blow into that balloon, the bigger the balloon's going to get. If you open up that balloon and you let some of the gas out, the volume's going to get smaller. Okay, so the volume and the amount of gas are directly proportional. So we can rearrange and say that the volume over the number of moles is constant. So therefore, the initial volume over the initial number of moles is equal to the final volume over the final number of moles. So let's work through a quick Avogadro's law problem. It's easy to remember this is Avogadro's law because Avogadro talks about moles, so it's the only relationship that has n, the number of moles in it. So take a moment to pause your video and work through this problem for Avogadro's law. Okay, the volume of a 0.25 moles of neon gas is 5.2 liters at a certain temperature and pressure. What is the volume after adding an additional 0.35 moles of neon gas? Okay, so Avogadro's law states that our initial volume over our initial number of moles is equal to our final volume over our final number of moles. So here we're trying to solve for our final volume. So rearranging the equation states that the final volume is equal to the initial volume times the final number of moles over our initial number of moles. All right, so if we input our information here, our initial volume is going to be our 5.2 liters. Our final volume, or our final number of moles, is going to be the summation of 0.25 moles we started with the 0.35 moles that we added in. So we add those two together to find 0.60 moles of gas over the amount of moles we started with, which is 0.25. And that's moles. Excuse me. So when we plug and chug here, we get a final answer with 2 sig figs of 12 liters. Okay, so a very simple relationship defining Avogadro's law. Okay, so we now have 3 separate gas laws that we've introduced here. Boyle's law, Charles' law, and Avogadro's law. Okay, so we have 3 different relationships that all come together to equal constants. Okay, so what happens if we combine all of these gas laws together? Okay, so we have our pressure times our volume is equal to a constant. We have our volume over our temperature is equal to a constant. And we have our volume over our N, our number of moles, is equal to a constant. Okay, so let's combine all these guys together. So we know P and V go together, and we know V is inversely related to T, and we know that V is inversely related to N. And so all of these guys together will form a new constant. And we can call this constant R, which is known as the gas constant. So if we rearrange this equation, we have the pressure times the volume is equal to the number of moles times a gas constant times temperature in Kelvin. Okay, so combining all 3 of these relationships, Boyle's law, Charles' law, and Avogadro's law, gives us PV equals nRT, which is defined as the ideal gas law, where R is the gas constant, and it's the same for all gases, and has a value of 0.082058 liters atmospheres over Kelvin mole. So let's take a look real quick and make sure that those units all make sense. Okay, so if we take a look at this notation up here on the board that we just wrote, so if we have R is equal to PV over NT, we know pressure has units of atmospheres, volume has units of liters, number of moles has units of moles, and temperature has units of Kelvin. And so if we take a look at our units provided on the slide, we can see that liters, atmospheres on top, kelvins and mole on the bottom. Okay, so the gas constant R makes sense and the units check out. And so the ideal gas law is a way of combining all 3 of these relationships together. And so it's important to know that the ideal gas law is for standard. So at you can sort of simplify the ideal gas law by talking about standard temperature and pressure, or what we call STP. And so whenever you talk about standard temperature and pressure, you're talking at temperature of 0 degrees Celsius, so 273.15 Kelvin, and we're talking about pressure at 1 atmosphere. Okay, so you can simplify that equation a little more if we're talking about standard temperature and pressure. Okay, so that concept will come back a little bit later. All right, so finally, let's sort of conceptually work through a few problems given our newly defined ideal gas law. So to the right is a cylinder which contains 0.5 moles of gas at 1 atmosphere of pressure and 250 Kelvin. Which of the figures below represents a situation where the amount of gas is 0.25 moles at 1 atmosphere of pressure and 500 Kelvin? Okay, so pause your video and try to work through that based on the ideal gas law. And I'll give you a hint here that you do not actually need to substitute any numbers in the equation. This is just simply a conceptual working with the ideal gas law. So pause your video and give it a shot. Okay, so let's take a look. So our correct answer here is going to be D. So let's see why that's true. So PV equals nRT. All right, so if we take a look at our number of moles, we're going to decrease our number of moles from 0.5 moles to 0.25. All right, so we're going to decrease the number of moles by 2. Okay, and our pressure, we go from 1 atmosphere of pressure to 1 atmosphere of pressure, so the pressure here stays the same. Next, we're looking at temperature. We go from 250 Kelvin to 500 Kelvin. So we're going to increase our temperature by 2 times. And so what we're actually looking here is we're comparing the change in volume. So if we change around and we're solving for volume, volume is equal to nRT over P. The pressure stays the same. Our number of moles go down by 2. Temperature goes up by 2. Constant stays the same. These two terms are going to cancel each other out, so we expect our volume to stay the same, which is answer D. Okay, next. When you increase the temperature of a constant volume of gas from 25 degrees Celsius to 50 degrees Celsius, the pressure of the gas does what? Okay, so pause your video and consider the answer. Okay, let's take a look here. So we are talking about the pressure of the gas. So if we're talking about PV equals nRT, we can rearrange and say that the pressure is equal to nRT over V. And so we're talking about here the number of moles and volume are all going to stay the same with the constant. So basically the pressure and the temperature being directly related to each other. So as we go from 25 degrees Celsius to 50 degrees Celsius, it seems like the temperature here is doubling. But if we think about the units that temperature has to be in for the ideal gas law, we actually see that these units have to be in Kelvin. So a transition here is going from 298.15 Kelvin up to 323.15 Kelvin for 50 degrees. So what we see here is actually not a doubling, not a quadrupling, not a half, not a remain the same. This is a change in pressure that is a value that's not listed here. Okay, so it's going to be a smaller change than defined here. Okay, so our answer here is E. All right, that's it for the day. Thank you.